Now we're in part 2 in terms of star magnitudes or brightness. The previous section was dealt with apparent brightness and how things appear on Earth in terms of brightness, and where the sun is the most bright object in our sky at a negative 25.6 little m for apparent magnitude. We abbreviate it little m, so it'd be minus 25.6 little m. And where the full moon's around a negative 12 on good conditions. Venus about a negative 1 little m. Sirius, even though this slide shows it a +1, is sitting at about a negative 1 also. And as far as our naked eye, where we have nothing to help us on a perfectly dark night in the country with no moon, up to about a +6. So now as I start getting more positive, it's dimmer. The more negative, the brighter. Pair of good field binoculars, you might be able to see it at a +12, depending on how much money you spent on them. Maybe a 13, so a little more than double what you can see without assistance. And our largest, most sophisticated land-based telescopes are about a +29 with an assist with orbiting telescopes. But that's the little m, or how it appears. The question is to be right next to them, how bright would they really be? What's their true brightness or absolute magnitude, which we signify by using the capital letter M in parentheses, in brackets. So how bright a star would be if it were 32.6 light years away from Earth, or 10 parsecs. And what we're looking at is what astronomers, through their instruments and through their studies, which we'll get into a little bit later, and you'll be able to do next week when we do Sky Map, is how bright would they really be if you could actually see them from 10 parsecs away. Remember our little video with Isaac Arthur took us to Proxima b, the planet, around Alpha Centauri group, and that was 4 light years, or a little over about 1.5 parsecs. So we're talking about almost 10 times that distance that he had in that video. So we're looking at what would it be if they were 10 parsecs away, how bright would these stars be? So if you line them up. So the absolute magnitude scale, shows it here from Earth, is if I could take all the stars and put them on an orbital path around us at 10 parsecs, how bright would they then appear to be? Because there are different distances now with the apparent brightness. So this little line shows that, hey, if we got 32.6 light years, if I lined up all the stars, how bright would they look? What would be their brightness? So we use the 32.6 light year standard because it's equal to 10 parsecs. Remember I said before, light years, as big as it is, about 66,000 astronomical units, it's still not a big enough measure. So we use the 10 parsecs. Again, 1 parsec equal about 3.26 light years, or 1 arc-second parallax distance from the Earth. That's that little triangle we looked at in the very first session. So we have Earth, and we line them all up, be 32.6 light years or 10 parsecs. It's a little bit easier number to remember. If the sun, with this negative 26.8 apparent magnitude, remember the brightest thing in our sky, if we were to take our sun and instead of 8 light minutes away, we moved it 32.6 light years out, or 10 parsecs, its absolute magnitude would be +5. So this is one of the ways we actually set the scale. What would our sun look like 10 parsecs from now? You can run a linear regression analysis on that. It's a mathematical model to take the output and then expand that light traveling that distance. So it's almost like a candle that you can use to measure everything else against. And most of the stars that we see or we've studied, even with the space telescopes that we talked about in the earlier session, will range anywhere from a -5. So that's a very bright star. If you think at 10 parsecs away, and it's still -5, half as bright as our moon, up to about a +15 absolute magnitude. So it's some really, really dim stars out there. So it puts the sun in about the mid-range of the absolute magnitudes, and it's +5. So between 5 and 15, -5 and 15, it's about halfway. So put a little sun out there, it'd only be a +5. So that's what it would look like. So now we're comparing that to what we're seeing with other stars. We can start teasing out how bright they would really be if we line them up at 10 parsecs also. So the relationship between the two measures, the apparent and absolute magnitude, depends on the distance between the Earth and the star. If a star is actually less than parsecs, like Alpha Centauri is less than 10 parsecs, or 2.6 light years, it may appear brighter they would if they were the actual distance. So Alpha Centauri appears brighter because it's only 1.5 parsecs away. But if we move it out 10 parsecs, it's going to obviously be dimmer because you're moving it away from you. It's going to get fainter. Thus, the apparent magnitudes are less than their absolute magnitudes. So anything less than 10 parsecs, its apparent magnitude, little m, is going to be less than the absolute big M. That's because you're moving it away, it's going to get dimmer. So our sun's apparent magnitude of negative 26.8 is less than its absolute magnitude of plus 5. Because I take that bright sun to us, because it's so close, and move it up to 10 parsecs, it's going to look pretty dim. So that's the relationship looking between these two. So the question is, how far away is a star with an apparent magnitude of plus 7 and an absolute magnitude of plus 7? Give you a few seconds to think about that. What if the little m and big equals big M? How far away would it be? Since they're both the same value, that means I don't have to move it to change it. It's 10 parsecs away. And so we're going to see this ratio is used to determine how far a star is, and then move it to that line to see what it looks like in reality. And that's the end of this for absolute magnitude. We're going to come back to